Good morning, students. Dear students, as in the previous video, we had discussed about an interesting application of Newton's law of motion, and that is the motion of a car on the flat road. We had discussed, and from there we had find out the relation for the motion of the car on the banked road without slipping, and after that we had calculated the optimum velocity by which the car will take the safe turn on the curved path. As we had studied in that, the centripetal force provided for the safe turn on the curved path by a car is given by the frictional force between the tire and the road. Now, in today's video, we will discuss about the centripetal force, that is the frictional force for the motion of the car on the banked road is provided by one component of its normal reaction, for which the car is, for which the road is bent and it is lifted from the outer edge with respect to the inner edge in such a way, so that the component of the normal reaction add to the frictional force and give the centripetal force, which due to which there is less wearing and tearing in the tire of the road. So, first of all, we will discuss about the application, motion of a car. Second application, motion of a car, motion of a car on banked road, motion of a car on banked road. In this, we will discuss about the banking of the curved road, banking of the curved road. When the outer edge of the road is lifted with respect to the inner edge, so that the friction between road and the tire is reduced. Road and tire is reduced to give less wear and tear in the tire. Means banking of curve provide the road of the Y at the sharp turn, at the position where the road is taking a sharp turn. At that position, the curved roads are bent. Means they are lifted from the outer edge and deeper in the inner edge. It is due to the fact that to reduce the friction between the road and the tire. And how the friction is reduced by the banking of the road, we will see in the derivation portion how it is reduced. And if the frictional force is reduced, it means to say that there is less wear and tear in the tire while taking the sharp turn on the curved road. Now, second thing is we will see about the angle of banking. Angle of banking. Angle of banking. Angle of banking. The angle by which the outer edge, the angle by which the outer edge of the curved root is lifted with respect to inner edge is called as angle of angle of banking. It means to say that suppose the road is curved here, and this is the outer edge and this is the inner edge of the road. So if the road is lifted in this way, then the outer edge is lifted in this way, then this angle is called as the angle of banking of the road. So we have discussed about the banking of curved road and the angle of banking. So the angle through which the outer edge of the curved road is raised above the inner edge is called as angle of banking. Now we will discuss about the derivation regarding the motion of the car on the banked road, and in this we will find out the angle of banking theta as well as the maximum velocity, as well as in this we will discuss about we will derive the angle of banking for the sector, that is theta, and also we will discuss for the maximum velocity with which the car move on the banked road in such a way that there will be a safe turn on the banked road by the car. So let us see the derivation regarding the motion of the car on the banked road. Now dear students, look at the motion of the car on the banked road. Suppose this is the curved road, and this is the flat part of the road joining the two edges. Now we have to lift it O, A, and this is the raised part. This angle is theta. So this is the raised part. Now look at here. This is a car which is traveling on the banked road. So here, since it is moving with a frictional force, F is acting in this direction. The frictional force F is acting in this direction. Now, this is the weight mg of the car on the flat road, and this reaction is the normal reaction which makes angle theta with the normal, So, this component of the normal reaction becomes r cos theta, and the another component of the normal reaction is r sin theta. Now look at here. Suppose this is the frictional force F. So suppose this is the horizontal component. So this component is r cos theta, then this component is r sin, this component is r sin theta. Now look at here. These are the two parallel lines. So on drawing the diagram of free body diagram for this, then what we will obtain? Suppose this is the weight mg, and this is the normal reaction. This component is r cos theta, and this component is r sin theta. Now, the frictional force F, this is OA. This frictional force F is making an angle theta with this. This part is gone. So since this angle is theta, this is the frictional force F. This is the frictional force F. So this angle is theta. So alternate interior angle, by alternate interior angle, this angle is also theta. By alternate interior angle, this angle is equal to this angle. So alternate interior angle F to the component of F along this direction is F cos theta. And this is F cos theta, and the component along this direction is F sin theta. Clear, students? The same here, r sin theta. So here F cos theta, and this is F sin theta. This is two diagrams. We had supposed here the car as the point object, and since we had supposed it as the point object, so we had resolved all these forces acting on this car. Now I am describing in the nutshell also. A car is moving on the bad road, so its weight mg is acting in downward direction. And normal reaction in this direction. So since it is elevated with angle theta, so from the normal reaction and shifted to angle theta. So this component is r cos theta, and the component in the horizontal direction is r sin theta. Now the frictional force is along this direction, so it makes angle theta. By alternate interior angle theta, then this angle is theta. So component of the frictional force along horizontal direction is F cos theta, and in the vertical direction is F sin theta. And the weight mg. Now, student, consider a car of mass m is moving with velocity v on a curved track of radius r, bent with angle theta. This is the situation. This is the situation which you are observing in the diagram. Now, if here there is no any vertical motion, since there is no any vertical motion. So since there is no any vertical motion, then what we will do? R cos theta is equal to F sin theta plus mg. R cos theta is equal to mg plus F sin theta. R cos theta is equal to mg sin theta plus R cos theta is equal to mg plus F sin theta. Suppose this is equation number 1. R cos theta is equal to mg plus F sin theta. Now, R in the horizontal direction, R sin theta, these are the forces R sin theta and F cos theta, R sin theta and F cos theta. And these, look at it, what I have told, these two forces, F cos theta, one component of the friction between the tire and the road, one component of the friction, that is F cos theta, along with the one component of the normal reaction R sin theta. These two will provide the frictional force and causes the centripetal force. These two combinedly, these two forces R sin theta plus F cos theta combinedly give the centripetal force, that is equal to mv square upon R. So from the second equation, R cos theta, R sin theta plus F cos theta, and it will give mv square upon R. This is the cause of centripetal force. Now we know that F is equal to, F is equal to mu s into R. In the case of friction, we have studied F is equal to mu s into R. So putting the value of friction, Fs mu s R in equation 1 and 2. So R cos theta is equal to mg plus mu s R sin theta, and R sin theta plus mu s R cos theta is equal to mv square upon R. mv square upon R. This is equation 5. So R sin theta, and from here now we are going to calculate the value of R. the value of R. This is equation 2, this is equation 3, and this is equation 4. From here, now we calculate the value of R from equation number 3. So from equation 3, we will calculate the value of R. Okay, dear students. Now we have derived the condition when the frictional force is 0, and if the frictional force is 0, then the value of Vmax is equal to Rg tan theta. Now, if the road is smooth and car has a velocity less than Vmax Rg tan theta, then the car will move inner edge of the road. Inner edge this side the car will move in this side if the velocity is less than Rg tan theta. Inner edge of the road, and if Vmax is greater than under root Rg tan theta, then car will move towards outer edge of the road. Means for driving the car on the road, on the track, it has the velocity Vmax is equal to Rg tan theta for a smooth road, and if there is the certain friction, then its velocity will be Rg tan theta plus mu s 1 minus mu s tan theta. If the velocity is less than under root Rg tan theta, then it will move inner side, and if the velocity is more than under root Rg tan theta, then it will move on the outer side. Now we will study about one topic. We will study about angle of banking. What is the minimum angle of banking for the car to make the safe turn on the road? That is the value of theta for the smooth road. So we have derived the condition, that is V square, the angle of banking, the angle of banking, that is equal to Vmax is equal to under root Rg tan theta, and from here Vmax square is equal to Rg tan theta. It implies that tan theta is equal to Vmax square upon Rg, or theta is equal to tan inverse Vmax square upon Rg. That is the angle of banking. That is the angle of banking provided to the car for making the safe turn. So this is all about the motion of the car on the banked road. Now in the next video we will discuss 2 or 3 numericals based on this, and after that this chapter 5 ends up, and we will start with the new chapter, that is work energy power. Thank you students, have a nice day.